Hello, welcome to class. Today we'll be covering how to approximate an integral that we may not be able to solve using elementary methods that we're used to. Things that we might be used to would be that of u sub, or using trigonometric substitution, and manipulating the equation in some way that we'd be able to solve it. However, there are some out there that we're unable to solve, such as these ones right here. And these are solvable, but not with the methods that we are currently knowledgeable of. So you might think that finding the antiderivative would lead to just a headache because we don't know of a way to actually integrate that. So what's the next best way to do? Well, that of approximation. We might not get the exact answer, but we can get close to it. And one prime example of this is looking at a graph here and see, instead of using what we're used to, which is rectangles, which tended to go above the curve and below the curve and wouldn't necessarily get close to the actual value, we can use a different geometric shape, that of being trapezoids. And the magic of trapezoids is that they're actually able to get closer to the curve than a regular rectangle would be. And if we were to add up all the areas of these rectangles under and above the curve, we would get closer to that value than using Riemann sums and those rectangles. And as you can see, we have split this graph up into various values, which we'll call n. And this simply works by grabbing trapezoids along the graph and using them in order to approximate the integral, or more or less the area under the curve, which is an integral. Now, the area of a trapezoid comes back to this equation that you might have learned before, which states that the two bases added together, then divided by 2 and multiplied by the height of that trapezoid will, in fact, give you that area. Now, if we were to take this and manipulate it in such a way to find the area of multiple trapezoids, we come to what is known familiar as the trapezoidal rule, as seen here. And what this basically states, and if I plug in this graph over here, is that we can actually take the number of values that we separate this graph into and plugging in that function for so many values, we can actually approximate the integral from a to b of any graph we want, that being f of x. Okay, and it's actually quite remarkable. Now, one pattern to see here is that for all graphs, we're going to be using this formula for the trapezoidal rule. We start off by simply finding how many numbers of n there are using b minus a. We want to find what the range is from. And we just divide this by 2 multiplied by n, which relates back to b minus a over n. And then over here, we're plugging in values for f of x for each value that we find. Now, one thing to observe here is that we initially just figure out that value, but then going on, we're going to multiply that value, multiply it by 2, until we get to that last value, which we don't multiply anymore. Okay, and this is derived from the manipulation of that area right there. Now, one way to see this is through an example. Now, here I have using the trapezoidal rule and approximate the integral of x squared from 0 to 6 using n equals 4. Now, if we were to take this equation we saw before and plug in those values, we get to here. So 0 would be your a, 6 would be your b. So 6 minus 0 will equal 6. And then 2 times whatever n value was asked. In this case, that n value is 4. We give it to you. So 2 times 4 equals 8. 6 over 8. That's easily going to be simplified to 3 over 4. Now, the more complicated part comes into this bracket right here, where we're plugging in x values, such as from 0 to 6, and evenly distributed form, like you would see in the graph that you saw before, even distribution. So if we plug in those different values and we split it up into 4 different parts, 0 to 6, we get 2 times 3 over 2 squared. As you can see in the function here, it's x squared. And then again, 2 over that next value, which happens to be 6 over 2 squared, and so on and so forth, until you get that last value, 6. And you just simply square it and you don't multiply it by 2. And this is the result we get. This is the approximation that we make. Now, this is pretty okay. But one way we can actually get closer to this is, instead of using trapezoids as we have been doing before, and using these, instead of using these geometric figures, we can actually use parabolas to gain a better understanding of what the integral might be. So as you can see here, there's a more a greater view of sine of x, but you can actually see that we have this function f of x, which you can think of as sine of x. We can actually approximate using a different graph, let's call it g of x, that gets closer and closer and closer to that curve. And you can find that area would be almost close to and approximately equivalent to that of f of x, the original equation. And again, we're doing it from a to b as your regular integral goes for different values of n as it's distributed. And this goes back to a concept known as Simpson's rule, which is an equation that looks similar, quite similar, and resembles that as the trapezoidal rule. However, Simpson's rule can only be used if n is an even integer, which is you need to take careful note of, and we'll come back when we're calculating values of n for a specific error minimum that we want. The only changes that you see is that 2 becomes a 3, and the pattern, instead of it being 2 times 2 times 2 and so forth, it actually changes here. It's 4 times 2 times 4 times 2 and so forth, until you get to that last one, which you don't multiply by anything, you just evaluate whatever that function is. You do that for both the start, as you can see here, and the end. One way to see this is through the example we did previously just now with the Simpson's rule. We're going to use that same function, that same integral, and approximate it even more. So 6 minus 0, we still get 6, but instead of using 2 times 4, we'll use 3 times 4, which is 12. So 6 over 12, that's a simple half. And then you go back, and instead of multiplying by 2, you'd multiply by 4. Then you add by 2 times whatever that function is, and so forth. Now, what makes this more simpler is the fact that if you're doing this on a calculator, it doesn't take much effort to go back and change those values that you had before, thus making it easier to calculate that Simpson's rule. And therefore you get this. Now, with every approximation, it's important to look at how accurate it is, and we can do that by taking and examining the error of both methods. T's of n relates to the trapezoidal rule, and S of n relates to the Simpson's rule. What you can find here is that the error relates to this formula right here, where you take your integral values from b minus a, and you cube that, and you multiply it, or you divide it, by 12 multiplied by whatever n value you have squared. The Simpson's rule is quite similar, except that these exponential values are obviously greater, considering it's far more accurate, and what you're dividing by is substantially greater than what you do with the trapezoidal rule. Now, these might confuse you for a bit, but we're going back into the realm of derivatives, where we grab f of x and we derive it, and we find what is the maximum value within that range that you were hunting between. And this could be done using the evaluating the endpoints of both b and a and finding which one is greater and plugging those in. Same goes for the Simpsons rule, where instead of using the second derivative, using the fourth derivative. And in doing so, we can actually estimate the error of using both. So if we have this equation, or this integral here, x squared plus 7x, evaluate from 0 to 2, where the n value is equal to 4, the first thing we'd want to do is actually evaluate what the derivatives are from the original equation to that of the fourth derivative. So we go from the original equation, a couple power rules, power rule again, until you get to 0, which is just fortunate of us because we don't have to do much later on. But if you were to evaluate using the original endpoints 0 to 2, and you evaluate which one is greater, you'll find that obviously 2 is greater, because, well, it's a linear equation, and the higher the number of x, the higher your y value would be. In this case, it's 11. And then when it comes to the fourth derivative, we're lucky enough that it comes to 0. So it doesn't matter what any number we plug in, we'll always get 0. That's just how it is. And then we'll plug this into the equations we saw earlier, these ones. We'll plug these in for both the trapezoidal and the Simpsons rule and find out how accurate or how far off we are using these estimates, both the trapezoidal and the Simpson rule. And we can actually see that the Simpsons rule is quite far more accurate than that of the trapezoidal, which this is just off by maybe 1/10. The Simpsons rule is quite on point. Now, these formulas can actually be even used more to see which n values might be used to gain a super accurate answer that you might want. And one prime example of this is right here, where we have this integral, radical x, evaluated from 1 to the 4th, and we want an error, let's just say the number we got earlier in estimating this error. We want these numbers to be, let's say, less than 0.00001, which is quite small, but can be quite important if we're applying it to physical concepts, maybe in fields of engineering or in everyday practices when you're trying to minimize that error and make sure your calculations are correct. So if we want to see what n value do we need to use in order to gain this minimization of the error, we can just plug it back into that equation we had been using before and actually evaluate n. So for radical x, the second derivative, the max point ended up being 1/4. And for the fourth derivative, that maximum point ended up being 15/6. So those will come into play using both the trapezoidal and the Simpsons rule, where we plug in that equation, including that max derivative that we saw earlier, and we actually end up solving for n. As you can see, when it comes to trapezoidal rule, n has to be at least 75 in order to even get remotely close to 0.0001. Whereas Simpson's rule, which happens to be far more accurate, you actually find that n has to at least be 12 in order to gain or to be equivalent to 0.001 in accuracy. So this just simply goes on to prove that Simpson's rule is far more accurate and far more useful than trapezoidal rule. And the reason this comes back to looking at the graph, where we see the trapezoids and the parabolas show different measures of accuracy. Where in trapezoids you have large gaps of white that are not covered in the trapezoids, leading to those errors, whereas the parabola tends to get closer and is actually on the graph itself, and is actually able to tell a far more accurate story than that of the trapezoidal method. And that's about it. That's covering approximation of integrals or numerical integration, which can be applied in multiple areas.